We have been discussing. Uh, Last time we tried to present a heuristic argument as to how showing the equation was necessary. And I'm going to use it. So today, we will advance the discussion a little further in terms of understanding states. So, uh, for that, we should first ask what is a quantum system? So, a quantum system, uh, colloquially, we will say that okay, this is for the time being, we will just consider that it's only a single particle, of course, with wave nature.
Excuse me, sir, your voice is not very clear.
Is that clear?
Yeah, now better.
I have to wind it around. Okay. So, is it better?
Yes, sir.
So, it's a single particle with its wave nature, or of course, we can take the suggestion of Eddington and call it some wave. So, this is our quantum system. Now, we have to talk about state of the system. So state is a very simple question. State of a physical system. You might have learned this in your classical.
Sir, your voice is breaking.
Hello.
Hello, sir. Can't hear anything.
Sir, I think you're muted.
Hello. Is this audible?
Yes,
Can
sir.
you hear me now?
Yes, sir.
Can you hear
Yes, sir.
continuously? Because I'm not seeing continuously
Yes,
Sir,
now.
sir.
sir, try to increase your microphone volume, sir.
Microphone volume. Okay. Is this better now?
Yes,
Yes,
sir.
sir, it's fine.
So let me share the screen again. So is the screen visible?
Yes,
Yes,
sir.
sir.
Okay. So in classical mechanics, you might have talked about the state and state of a system in classical mechanics is so if you have in classical mechanics, if you say you have a system which is also a single particle, then you will talk about the state. Let's say in one dimension to be very simple and specific. Then for such a system, you define the state to be simply the value of its generalized coordinate and its generalized moment. So some canonical pair of position and momentum observables, position and momentum coordinates will define the state. Okay, so in the same way, if you are talking about thermodynamics, for example, thermodynamics, you have a macroscopic system. The system is a gas or a liquid or something like that, which is macroscopic. You don't have to bother about whether it is made up of particles or not. So in thermodynamics, you have this. Then you say the state is basically given by pressure, volume, temperature. For example, it can be some other properties also. But these properties essentially, in some sense, how do we define a state? The minimum set of properties that are required to describe any other property. So pressure, volume, temperature, if I give you, then probably all thermodynamic quantities can be obtained from that. Or you may choose some other properties. Maybe you choose energy, volume, and amount of substance, or the mass of gas, or something like that. So you could actually choose any set, but some minimum set that describes the entire, all the other properties of the system. We will call it as the state of a physical system. Now here in quantum system, okay, so for a quantum system, as we have identified, that system could be a single particle with wave nature or a vehicle. Quantum system, the state is given by or represented by the wave function. Okay, so we talked about what a wave function is yesterday. That is a complex valued function of x and t. Okay, I'm still continuing with one space, one time dimension. If it is three space, then you have x, y, z, and t and c. So the wave function that we talked about in the last class is basically very important, because that is what tells you the state of the system. What does that mean? That means if somebody gives you the wave function, then that means everything about the system can be calculated. At least the information about the system is completely contained in the wave function. Okay, so that is why it is very important, and it is called the state of the system. Okay, now we have of course talked about the interpretation of this wave function last time, and we said Max Born had come up with an interpretation relating this wave function to what is called the probability of existence of the particles at some location at some time and things like that. Okay, so let's not worry about it at this moment. So let us say that you have some psi of x comma t. Okay. So this is a symbol that we always use. It is so commonly used that even if you use psi in some other subjects, people think that you are doing quantum mechanics. So quantum mechanics is identified with this psi, so much so that psi is synonymous to quantum mechanics. So this is what is called wave function, and this also has another name, as I told you, or it is also called probability probability amplitude. Okay. So I will talk about this probability amplitude little later, but this wave function has to be understood. Okay, so now the question that we are trying to ask is, this is the wave function. This represents the state of the particle. Okay, now we can ask a question that supposing if you have, so what kind of, so this is state. Okay, now in classical mechanics, let's say a point q comma p is the state. I'm going back to classical mechanics again and again because it is always good to go from known to unknown. So in classical mechanics, QP is the state. Okay. Now set of all states. Okay, set of all states. That means set of all points of QP becomes a space. Okay, so we call this as phase space, right? Phase space. Phase space. So now we can ask the question: what happens to set of all states of a quantum system? Okay, so we can talk about so what is the state space of a quantum system? And for the discussion of today and maybe a few more classes, even though I write quantum system, please understand that it is a single particle with a wave nature. I'm not going to talk about many particles in the immediate future. So whenever I say quantum system, even for the generality purpose, please understand that that system is a single particle. Okay. So what is the state space of this quantum particle? So that is the question that we are going to be worried about. Now, to understand this, we have to learn a little bit of mathematics. So some mathematics is required. Okay, so I'm going to do a kind of a crash introduction of that mathematics that is required, and you probably will study it in more detail in your Mathematical Physics 2 course, which is currently going on, because your first 2 chapters is on the mathematics required to describe quantum state space. Okay, so of course I am teaching you the last chapter, but first 2 chapters you will learn the mathematics required, but I will give you a small capsule or a summary of the mathematics that is required. So we have to learn certain notions. Okay, so some concepts. Okay, some mathematics, some mathematical notions. Okay. First, we will talk about a vector. Okay, we should understand what a vector is. And then we talk about something called a vector space. Vector space. And then we talk about something called an inner product space. Okay. And then we talk about what is called a Hilbert space. Okay. And we make a claim that what is the state space of a quantum system? Okay, so the answer to that question turns out that it is is a Hilbert space. So to understand that one, to understand this answer, we have to have the mathematical notions of this. Okay. So the state space of a quantum system is a Hilbert space. Okay. Now it is easier said than done. So after we have got certain idea of these notions, then we are going to present some kind of an elegant notation in which you can do quantum mechanics, elegant notation to do quantum mechanics in abstract sense or abstract way, and this notation is called Dirac-Rachet notation. Okay, we introduce this notation so that you can do quantum mechanics in this notation. But during our course, we interchangeably use the wave function notation, Dirac bracket notation, and what is the other notation? That is wave function. Wave function notation. Okay, so let me simply call it as wave function notation. Now we may interchangeably use these things, but once you know how to go from here to here and here to here, or what is the correspondence between these two notations, then it doesn't matter. Whichever you are comfortable, you can use that, or whichever is more convenient in the context, you can use that. Okay, so that is our aim of today's lecture. So now let us try to start. So I'm going to I'm not going to follow any rigorous way of introducing these things, but I will more or less follow some heuristic way of introducing these things. Okay, so because the aim is you should get a feel for these concepts, and then later, if you are interested in rigorous theorems and proofs, you can do that. So first, I will talk about a vector. Now, as I told you, we will always go from known to unknown. So we have a vector, and we think we know vectors. For example, vector in three-dimensional space. Okay, 3D. So what you do, you denote this vector by a kind of arrow on this, because this we are used to, right? Denote it by an arrow. And you can write it, you can just leave it like that, or you may say, okay, this is my vector. Okay, or you can say that, okay, I have a coordinate system and this is my vector. Okay, so this vector can be just drawn as an arrow, or it can be, so I can choose some XYZ coordinate system, and then I can realize this vector as an arrow in this. What is the advantage of choosing this coordinate system? If I choose this coordinate system, then I will be able to write this A vector in components. So I can say I have some AX. Okay, so let us call EX is the unit vector along X direction, plus AY. EY is the unit vector along Y direction, and EZ is the unit vector along Z direction. Okay. Now, what is the difference between writing a vector like this and writing a vector like this, or representing a vector in a coordinate system and representing a vector like this. So if you realize that these two are kind of a abstract vectors, in the sense, for example, if I choose, okay, so let's say instead of a coordinate system like this, let's say I choose another coordinate system. So let me say I have a different coordinate system. So let me call this as x prime, this is y prime, and this is z prime. Then what happens? The same vector A will now be written as some ax prime ex prime cap plus ay prime ey prime cap plus az prime ez prime cap. Okay, this is understandable. Okay, so here we say that this ax ay az, ax comma ay comma az, what do we call them? These are called components of the vector. Components of the vector. Okay, now as you can see, components of a vector, depend on the choice of coordinate system. Choice of coordinate system. Now, when we are studying vectors, suppose let's say that I don't want to choose any coordinate system. I can still do something about vectors. For example, let us say that so what can we do? You can actually say that, okay, I want to do vector algebra without choosing any coordinate system. For example, let's say that I have a relation between vectors like this. Let's say a vector C is equal to vector A plus vector B. Now, this relation between two vectors or addition of two vectors, I could have represented geometrically in this fashion. So suppose I have a vector A like this, and then I have a vector B like this, and then this is the vector C. Now, this way of representing these vectors is independent of any coordinate system. The parallelogram law of addition of vectors is not depending on any coordinate system. So what happens? Suppose if you choose a coordinate system, then A will have different components in that coordinate system. A will have some components, B will have some components. When you add the components, you will get the components of C. So if you say AX plus BX is CX, AX prime plus BX prime will be CX prime. Okay, so this addition formula that I am writing here is independent of the choice of coordinate system. Similarly, suppose if I have A dot B, okay, so let's say I have a dot product like this. Now I can say this is nothing but modulus of A into modulus of B into cos of the angle between A and B. Suppose I say like this, that is, I have A and I have B, and this is the angle theta. I can say like this. Now, this statement of the dot product does not depend on coordinate system, correct? Does not depend on the coordinate system. Okay, whereas I could have written A dot B as AX BX plus AY BY plus AZ BZ. Even though AX, AY, AZ, BX, BY, BZ will change with the coordinate system, but when you take a product and sum them like this, you will get same number. So which is same as, which is also equal to AX prime BX prime plus AY prime BY prime plus AZ prime BZ prime. So that means this result, this A dot B, doesn't depend on the choice of the coordinate system. So we should be able to write it in a coordinate independent fashion. Okay, so you can see that the vectors. So please recognize, maybe sometimes you did not recognize this when you are studying vectors. Now when you are studying vectors in your mathematical physics course, I want you to recognize that which are the relations that don't depend on the coordinate system, which are the relations that depend on the coordinate system. Okay, so that I want you to keep track of. Now I want to introduce, so let me just say that, so represent a vector A, represent a vector like this A as AX EX plus AY EY plus AZ EZ. Okay, this vector A as, I'm going to now simply try to introduce a new symbol. So the same A, I'm just going to call this as A. Okay. We will come back to this, and I will simply give a name called ket here. Okay. I will simply give a name called ket. Now, what is this ket? This ket I'm going to define. Okay, this ket I'm going to define as AX, AY, AZ. I'm going to define this as a column matrix. Okay, so this as a column matrix. Okay. Now, this is abstract. When I say abstract, what does it mean? That means it is independent of the choice of coordinate system. And whereas this one, these are components, correct? So these components depend on coordinates. So you choose x, y, z coordinates, or x prime, y prime, z prime coordinates. Now, whatever coordinate system you choose, this right hand side keeps varying, but left hand side has got some solidity, right? So it is not whatever is your left hand side, this vector or this ket what you defined here, or a vector in general, which is an arrow, is going to be the same. Okay, so you are going to describe it differently depending on the choice of your coordinate system, but that is one vector or one. So we are going to call this. So whatever is the vector that we are familiar with with a letter and an arrow on the top, we are going to call this a ket here. In fact, uh, I am little fond of introducing it in this way. So let us say that I have a vector and let me draw my arrow in this fashion. And now what I will do is I will I will slowly erase this line. Okay, so I think I have not erased it properly. Suppose this is the vector. Now I erase this arrow, and then I slide this A and then put it here. Okay, so this is the most classical to quantum transition in a continuous manner that I can do. Okay. Okay. Please don't take this seriously. This is just a way to tell a story so that you don't think that there is a much difference between what a vector that we represent like this and ket. So this is what I am going to call a ket. We will formally come to ket vectors later, but if I want you to understand right in the beginning that it's not a very difficult concept to understand. That is why I'm introducing right at this level, that when we talk about a vector. Now, so what is it that we have learned so far about vectors? What we have learned is that a vector can be handled by choosing a coordinate system, and it can be handled without choosing a coordinate system. And there are certain relations or certain algebra and calculus that you can do with vectors without bothering about the coordinate system. Okay, these are the two ways in which we can handle this. And we used to simply write an arrow on the top of a letter to represent a vector, which is independent of coordinate system. Same thing we will represent with a ket. Okay, for a change from now onwards. So when we say ket, we don't care about the coordinate system. You choose a coordinate system, then this ket can be written as a column vector. Okay, so you choose a coordinate system, a ket becomes a column vector. That is the only thing that I want you to take home from here. Okay, now some generalization of the notion of vector. Okay, so let us say that the notion of a vector is more general. Okay, so let us see what is the more general notion. Okay, so for that we have to define some kind of a structures. Okay, so we have talked about. I am borrowing some knowledge that we have gained from our mathematical physics course. So let us say that I have, let's say I have a set. Okay, so consider a set. Let's call that as capital X, which has got certain x1, x2, etc. Okay. Now, we know that under certain conditions, this x with some binary operation that we have defined, okay, So this is a binary operation of elements of X. Binary operation is a group if I'm not going to write them again. So 1, 2, 3, 4 are satisfied. Okay. So I'm sure these 4 conditions are in your memory. First is closure property, second is associative, third is existence of identity, and fourth is existence of enemy. If all these 4 axioms are satisfied, then this is called a group. In addition, a fifth property called xij, okay, or xi composer xj is equal to xj composer xi for condition for all xi comma xj in X. Then what do we say? Then we say this X O is an abelian. Now, so this is the concept of a group, which we already know. So I am just introducing. So this is what is called a group. Now, let us consider a set. Consider a set. I'm going to call this set as F. Okay, consider a set F and 2 binary operations. Okay, and addition, that is usual addition that we have, and multiplication. Multiplication, which let me call it as some dot. So addition and multiplication as 2 binary operations. Okay, so we are now introducing a different notion. So we have a set F and addition and multiplication as 2 binary operations. Now we are going to talk about an algebraic structure F plus and this dot multiplication. Okay. Now there is a concept called a field. Okay. A field if the following axioms are satisfied. What are the following things? First one is that F with plus, if you just consider with this, is an abelian group. Is an abelian. Second, that means this will satisfy all those 4 axioms, 5 axioms. Second, you consider F and remove 0 from that. That is F minus 0 with this multiplication is an abelian group. So you might understand why we are removing 0, because if you put 0, then inverse for 0 is a problem. Okay, and what is this 0? So here 0 is an additive identity. So if you are removing 0 when you are multiplying, multiplication is the binary operation, that's okay, because 1 is the multiplicative identity and 0 is the additive identity. So that can be removed. Okay, and then there is a third set of properties that it should satisfy. That is, so let's say that you have let's say that you have, suppose you have, let's say, alpha, beta, and gamma. Let's say these are some three members of this F. Then you can say that this alpha plus beta multiplied with gamma, alpha plus beta multiplied with gamma. That means, you see, in this third only we are mixing these two binary operations. In first we are using plus as the binary operation. In second we are using multiplication as the binary operation. Now we are trying to mix these two binary operations. So this is such that this is like alpha multiplied with gamma plus beta multiplied with gamma, and the results are added. Okay? The results are added. So this is called the distributive property. Distributive property. Okay. So if any set of numbers that satisfy these three groups of conditions, then we say it is a field. Okay. So some of the examples of fields. Okay, so you take set of all rational numbers. Set of all rational numbers. Okay, so I will leave it for you to verify. Set of all rational numbers or set of all real numbers. Set of all real numbers and set of all complex numbers. Okay, so these are some examples of. There are more examples, but let's simply consider these examples for the time being. These are fields. Okay. Now, once we understand the definition of, see, please remember, to understand the definition of a field, we require the definition of a group. That is why I introduced the group first. Then for field, you have to have F plus has to be a field, F minus 0 dot has to be an abelian, this has to be a abelian group, these two are abelian groups, then it should have a distributive property. Okay.
Sir,
now, yes.
Sir, in this case, if we have in this field, we have two binary operations, plus and dot. But in
Correct.
group, we used to have only one binary operation. Does it make
Correct.
a difference or?
Yeah. For a field, you require two operations.
Okay. For group, one is enough.
Yeah.
Okay. Yeah. Thank you, sir.
Okay. So now we are ready to define. So now we are ready to define what is called a vector space. Yeah. So we are going to now define what is called a vector space. So here we have two sets. First thing is V. This is what is called a set of vectors. Okay. Then we have a binary operation plus, and this plus is basically vector addition. Vector addition. That is addition of two vectors. Then we have F. Okay, so we call this as a set of scalars. And this field, this is a field, or sometimes you can call this as, so this is a field. Okay, and this field will have two operations, right? So field will have plus and dot. These are two operations. Okay, so that is what we call as scalar addition and scalar multiplication. These have two problems. So now we have an algebraic structure like this. The structure is that you have V, and I'm going to call this as plus, but of course I'm not going to write this plus minus and all that, because we already know that plus minus should be there if you have to have this to be a field. Okay, so at this moment this is set of vectors. Okay, this is set of vectors, and this is vector addition, and this is field of scalars. That means already the scalar addition and scalar multiplication are there in that, because then only we can define a field. Okay, now this is a vector space. So this is a vector space if we have the following things. First, this V with this plus is an abelian group. So the first set of conditions are same 1 to 5 conditions that we have for a group. So V plus, this V is a set of vectors and plus is a vector addition, and with respect to this it has to be an abelian group. Now second is, now we have to talk about the properties of F and some combination of this F and V. So suppose, let us say that I have alpha in F. Okay, alpha is a scalar variable from the field, and let us say that I have A and B are two vectors. I am not even writing this what is called a arrow now, because I'm just saying these are two different elements. Okay. Now, if you ask a question, what will be alpha? Okay, so I think before that I have to write one more thing. So let me just do that. Okay, so before that, for any alpha in F and A in B, alpha dot A will be also in B. This is called, this vector space V is closed under, okay, so it is said that it is closed under scalar multiplication. Okay, so it doesn't mean that we are defining a kind of scalar multiplication among vectors. If you take a field variable and then multiply it with a vector, that will be another vector in the vector space. Okay, so this is let us say first condition of the second group. Then we have something like this, that is, given alpha in the field and A comma B in V, so we can talk about alpha dot A plus B. This is a vector addition, right? Is same as alpha dot A plus beta dot B. So we say that scalar multiplication,
Sir, alpha dot B, sir.
alpha dot scalar multiplication is distributive. That is what it means. Scalar multiplication is distributive. It can distribute between these vectors. Okay, so you multiply with A and multiply with B separately and add the resulting two vectors. We already said that if alpha dot A is also in V, and that will be a resultant vector in V, and that vector can be obtained by simply doing this. So this is a distributive property. Okay. Now you can also, okay, this I think is enough to state that this becomes a vector space. Okay. So now let us try to understand. Let us try to understand this vector space. Again, so some of the things that we are familiar. Okay. For example, some simple examples. Okay. So let us say that we have vectors which is equal to, let's say, x ex plus y ey, such that x and y are real numbers. Okay, suppose we define like this. Okay, so this is my set of all vectors on a plane, right? If you take a plane, then every point you can draw an arrow from the origin of the coordinate system, in case we choose a coordinate system. Otherwise, every point on the plane is something like this. So this I can also write it in the following fashion. So I can define this V as a column vector or a column matrix x comma y, such that x, y belong to real numbers. Okay. Mathematically, this kind of a vector, this kind of a set is called R2. Just to say that there are two real numbers. X is one real number, Y is another real number. This is called R2. This is another name which is usually used in the books. Okay. So this is a vector space. Okay. So now you can see that X is a real number. So what is the field? So here the field is the set of real numbers. Field is set of real numbers. Okay, this is one simple example. Or you can think of a simple set of real numbers itself is a vector space. If you consider set of real numbers. So this is one example. Okay, so this is one example. Or you can have three-dimensional space. That is, you can say V is equal to, you have X, Y, Z, such that X, Y, Z are real numbers. You define this as some R3. Okay, R3, because there are three real numbers. So one can generalize this and then say that you can have Rn, an n-dimensional space, which is given by x1, x2, etc., xn, such that xi is a real number for all I equal to 1 to n. Okay, so this is something one can imagine that. So this is inconsistent with our notion of vectors, because I can have two-dimensional vector, three-dimensional vector, n-dimensional vector, and things like that. Okay, but then I can also talk about. So let us say that. So this is. So these examples. These examples are in line with our notion of vector. Okay. Now let us look at an example like this. V is equal to, let's say, I have A, B, C, D, such that A, B, C, D are all real numbers. Okay. Now here this plus is basically a matrix addition. Now you can show that. I will leave this as an exercise. Show that this is a vector space. That means it will satisfy all those axioms that are required for the vector space. Now, what does that mean? That means here a 2 by 2 matrix, a 2 by 2 real matrix is an element of the vector space, and therefore is a vector. Okay, so now you may say, come on, you are talking about a matrix and why you want to call it a vector? That is what I'm calling it as a generalization. When we say there is some vector space, every element of a vector space is a vector. It may be a matrix, it may be something else, but every element of that is basically a vector. Okay. Let's look at another example. So consider set of all polynomials, of order less than or equal to 2. That means constants, linear polynomials, and quadratic polynomials. Okay, so that means what I'm going to have V as defined as some A naught plus A1x plus A2x square, such that A0, A1, A2 are real numbers and x is also a real number. That means what? So suppose, let's say that I have a plane. Okay. Maybe I think I should simply look at. So let me just modify this even to. Okay, so let us simply say that set of alpha order less than or less than 2. Then what happens? It is only A0 plus A1x, like that. Now, what does that mean? That means that suppose you have some x and y. So A0 plus A1x is what? This is a straight line there can be another straight line. This is 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 another straight line. Like so, this equation or the set is set of all straight lines. Set of all straight lines on a plane. So, if you consider set of all straight lines on a plane, then you can say, okay, I add two lines, I get another line. I add another. So you can show that this will form. So now you have to talk about, of course, what do you mean by addition of two lines? So addition of two lines you have to define. Okay, so let's say this is addition. Earlier we said it is matrix addition. We know what it is. So addition of two straight lines. Two straight lines is basically a pointwise addition. Pointwise addition. That means, let us say simply we have something like this. Let's say y is equal to, so this is y is equal to 1. And then let's say this is y is equal to 2. So what is the addition of these two lines? That will be 1 plus 2. So that will be equal to y is equal to 3. Y is equal to 3. So you add this line and this line, you will get this line. So like that, you have to simply do a pointwise addition. So you define a vector addition like this, then you can see that this will be a vector space. Okay, so show that this is a vector space. So what is a vector here? A vector here is a straight line. Okay, you could have also talked about vector space of functions like this: a0 plus a1x plus a2x square, such that a0, a1, a2 belong to real numbers and x is a real number. So if you take this, this also will be a vector space. Okay, but then what is a vector here? Vector here is a quadratic curve, right? So it's a quadratic curve. So a vector is now a curve, right? So like that, we can talk about vectors. We can generalize the notion of vectors depending on a vector space. Okay, so now I want to introduce an important notion called the dimension of the vector space. Okay, so we have to define. So let us find the dimension of the vector space. Okay, so you know how to define this dimension of the vector space. There are certain important notions that we should understand before you define the dimension. So first thing we have to understand is something called linear dependence and linear independence of the vectors. Linear dependence and linear independence of vectors. Now we know vectors are not just arrows. Vectors can be matrices. Vectors can be curves. Vector can be straight lines. So we have now generalized that. Now let us try to understand this linear dependence and linear independence. Let's again go back to our vectors. Suppose if I have a vector like this, And then I have another vector which is along the same direction. Okay, so let us say that I have another vector which is like this, along the same direction. So we will call this vector as B, and we will call this vector as A. Okay, now what I can do, since A and B are in the same direction, I can stretch it little bit and then make A into B. In other words, this picture tells me this vector B can be obtained from vector A by multiplying with some scalar. Okay, that is, we can get B from A by multiplying a suitable scalar. Maybe this is the scalar is 3.154, or it may be 0.670 if it is shorter, and things like that. So whenever you can obtain one vector from the other vector, we say that, so if we can do that, then we say that A and B are linearly dependent. Okay. This notion is very important. So if they are linearly dependent, that means what? You can get one from the other. Now let us generalize this notion, or let's say that we have a situation like this. I have A here, and there is a vector B in some other direction. Okay. Now you can see that whatever I multiply A, I cannot get B, because they are in different directions. Because I can imagine that I will decompose this A. Okay, so you may see that in vectors we write like, this is the projection of A along B, and then there will be some. So that means this is like B, but there will be something which is perpendicular to B. Those two are together only this vector, right? So you can multiply something to this to get B, but then there is a component here, no, which cannot be. Whatever you multiply with that, it is going to not add to this B. So if the vectors are like this, okay, so we call them as two non-collinear vectors. Two non-collinear vectors on a plane are linearly independent. So we understand this notionally, but let us try to develop a kind of mathematical statement corresponding to this. Okay, so let us say that let's take some linear combination of this A and B. That means, let's say that I have alpha A plus beta B. Okay, alpha A plus beta B. Let's say this is equal to 0. Okay, this is a 0 vector. That means alpha A and beta B has to be 0. What does that mean? Alpha times A should be equal to minus beta times B. Correct? That is what it means, right? Okay. Alpha A and beta B is equal to 0 implies this alpha times A should be equal to minus beta times B. Correct? Or in other words, this implies A is equal to minus beta by alpha. See, beta is some field variable, alpha is some field variable, minus beta by alpha is some field variable. So this implies we have now achieved what is called A is equal to, let us call this as some gamma times B. What does that mean? That means they are linearly independent. So now this equation, see, note that A is not a zero vector, A is not a zero vector, B is not a zero vector. These are two non-zero vectors. Okay. Now, if I want this to be equal to 0, if I want this to be equal to 0, the only way this can be equal to 0 if these two are linearly independent is both alpha and beta have to be 0. Okay. So the definition of linear independence. Okay. So A and B are linearly independent. Let me write it shorthand like this. Linearly independent implies, so if for alpha A plus beta B, alpha A plus beta B is equal to 0, implies alpha equal to 0 and beta is equal to 0. Only then they are called linearly independent. Suppose if they are not 0, then we can argue like this and show they are linearly dependent, which is a contradiction to our assumption that they are linearly independent. So this is a useful mathematical criteria to see whether, to check whether a given set of vectors are linearly independent. Now this can be generalized. Okay, so this can be generalized. Can be generalized to a set of vectors. Same notion can be generalized. Suppose consider, so a set of vectors so let me call them as v1, v2, etc. some vn. Okay, I'm not even putting these arrows here. Okay, so they belong to this set of vector space V, are linearly independent. Okay, if alpha 1 v1 plus alpha 2 v2 plus etc. alpha n vn is equal to 0, implies alpha 1 equal to alpha 2 equal to alpha n is equal to 0. This is the only solution. If the whole sum is 0, this is the only way it can become 0. Then we say that they are linearly independent vectors. Now, the linear independence is very important notion because as we have once again seen in the case of plane and space like that, the dimension of the vector space. Okay, so for example, you can say that so for a given vector space, for a given vector space, V, the maximal set of linearly independent vectors. Maximal set of linearly independent vectors. What do we mean by maximal set of linearly independent vectors? That means for a plane, for example, I write A and another vector B, which is not along A. Then I have A and B. These two are linearly independent, as we have discussed. But then you write another vector C on the plane, we can always write it as a linear combination of A and B. Okay, that means a set of 3 vectors is always linearly dependent on a plane. In the same way, a set of 4 vectors is always linearly dependent on in a 3-dimensional space. So you see that there is some kind of a maximal set of linearly independent vectors. Okay. And beyond that, if you add another vector to that set, it is going to be linearly dependent. So the maximal set of linearly independent vectors is called a basis. Now this maximal set of linearly independent vector is you can choose any vectors. No, so the basis is not unique. This is very important. So basis is not unique. Now I want to connect what we started with. So the coordinate system that we have talked about earlier, the coordinate system is actually the choice of basis. Defines the basis. Okay, you say that you take XYZ coordinate system, then EX, EY, EZ are the basis elements. You take X prime, Y prime, Z prime coordinate systems, then EX prime, EY prime, EZ prime are the basis elements, and things like that. So coordinate system is basically the choice of basis. And basis is not unique, just like coordinate system is not unique. Okay. And now we are ready to define the dimension. So then the cardinality of the basis. Okay, so the number of elements are the cardinality of the basis is the dimension. Dimension of the okay. Now, so once we say that we have a basis, okay. So let's say that I have a vector space V, okay, and then I have a basis B, which is given by, let us say, vector B1, B2, etc. Let's say some Bn. Okay, so there are n elements in this. So what is the dimension of V? Dimension of V is equal to n. Now, once you choose this basis, okay, so any arbitrary vector belonging to this vector space, okay, suppose if I add this vector to this set, okay, any arbitrary V in V, okay, so for any arbitrary V in V, the set V comma B1 comma B2 etc. Bn, is it linearly independent or linearly dependent?
V is linear dependent, sir.
Huh?
V is linear dependent, isn't
No,
it?
this set,
Because
linear dependent or independence is with respect to set. So this set is linearly dependent or linearly independent?
Dependent.
This is linearly dependent. That means, so this is linearly dependent. Okay. But since this is a basis, B1, B2, B3 are linearly independent. So what does that mean? That implies your V can be written as some coefficients, let me call that as Ci into Bi. I is equal to 1 to n. That means every element of the vector space can be written as a linear combination of the basis elements. Okay. Now, if you choose another basis, these components will change. That's all. Okay. So here what we say is that Ci is the component of B along the basis element Bi. Basis element is like a unit vector. Okay, so Ci is the component of B along the basis element Bi. If I choose another basis, some B1 prime, B2 prime, B3 prime, then these components will change. So this is the same notion as we have seen earlier. Now there is a useful a useful notion or a useful idea which will help us to understand the dimensions quickly. Now this understanding that every vector is represented as a basis elements. Now what are these Ci's? These components, so note that Ci are scalars from the field. Okay. So we can have this useful idea. The idea is something like this. The dimension of a vector space, the dimension of a vector space is equal to the number of scalars from the field required to represent an arbitrary vector in the vector space. Because you know the dimension of the vector space is the number of elements in the basis, and anyway to represent an arbitrary vector you must multiply each basis with a scalar. So that is why the number of scalars required to describe an arbitrary vector is called the dimension of the vector space. Okay, I'm actually not saying anything new. I'm just reversing this argument and then saying it like this. But then you will notice that this way of saying has certain advantage in finding out. So let me give you an example how this can be of much use. So let us say that. So let us look at an example like this. So consider a vector space. Okay, so let's say you have a vector space which is equal to A, B, C, D. We have talked about this earlier. A, B, C, D are real numbers. Okay. Now tell me, what is the dimension of this vector space? The dimension of this vector space. What is the dimension of this vector space? Or what is the field here?
The dimension is 2.
Dimension is 2. Why do you get 2? How did you get 2?
Because I can use a column vector which has 2 rows to completely represent this 4 by 2 cross 2
2 by 2.
matrix.
Okay. So that is one answer. Any other answers? Okay. So let us try to understand this. Your silence seems to be. So let us look at a slightly simpler vector space. So let us come back to this. Let's say I have V, which is equal to, let's say, A, E, such that A and B are in real numbers. What is the dimension of this vector space?
Two, sir.
This is 2. Why this is 2? Because these are set of points on a plane, correct? And there are 2 linearly independent vectors. What are the 2 linearly independent vectors that you can think of? You can think of many, but then one set of 2 linearly independent vectors you can think of is 1, 0, 0, 1. These are basically orthogonal vectors, right? So 1, 0 and 0, 1 are, one is along x, other is along y. Correct. So this is a 2-dimensional space. But what I am trying to tell you using this is that any vector AB, okay, has to be written as A times 1, 0 plus B times 0, 1. So I require 2 scalars, A and B, to represent an arbitrary vector AB. Since I require 2 vectors, the dimension is, 2 scalars, the dimension is 2. So that is this useful idea that I have talked about here. Okay. So the dimension of a vector space is equal to the number of scalars from the field required to represent an arbitrary vector in the vector space. Now, let us come back to this. What is the vector here? Vector is a matrix. And how many scalars are required to describe this matrix?
Four, sir.
4. So what should be the dimension? It has to be 4.
4.
So this is a 4-dimensional vector space. Okay. A 2 by 2 matrix is a 4-dimensional vector. So it's a 4-dimensional vector space. Okay. Is that clear to everybody? So you can see already there is an advantage of this idea that if you are given a matrix without even writing down what are the linearly independent set, you know how many real numbers are required to define a 2 by 2 matrix. That is enough to tell you what the dimension of the vector space is. Okay, so let us try to understand this, or to make this idea more concrete. Let me look at this example. Let's say I have V as set of, so V is a set of 2 by 2 symmetric matrices. Symmetric matrices. What is a symmetric matrix? A matrix is A is symmetric if A transpose is same as A, right? A transpose is same as A. That is the definition of a symmetric matrix. Now I want a set of matrices which are symmetric matrices. So how do I write that set? I will say that I have, so A, B, C, D, suppose you take A, B, C, D, and you take a transpose of A, B, C, D, what will that be? A, C, B, D. Okay. So you want to have the same, it should be same means what? your B and C have to be same. So that means I'm going to have A, B, B, C, such that A, B, C will be equal to, they are in real numbers. So what is the dimension of this vector space?
2.
Huh?
2.
I couldn't hear you.
So is it 2?
Why?
Because B can represent this by 2 scalar matrix.
We can?
We can represent it with the help of 2 scalar matrix.
What are the two scalar matrices?
So one can be 1 0 0 0, another can be 0 0 0 1.
Say that again. 1 0 0 0
0 0. Another is 0 0 0 1.
0 1. Okay. So if you use these two, can you construct all symmetric matrices?
Yes, sir, I think.
For example, let us take some A times 1 0 0 0 plus B times 0 0 0 1. Then what will I get? I will get A 0 0 B, right? You will only get those matrices that are diagonal and symmetric. But symmetric matrix need not be diagonal. Correct? So you will not get all those non-diagonal symmetric matrices at all.
Sir, dimension will be 3.
Dimension is 3. How did you come to this conclusion?
Sir, there are 3 elements.
So that is what I am saying, that it is always easy to get to the dimension 3 because we require 3 scalars, because I know A, B, C, and I require A, I require B, I require C to write a so either if you are able to write a general vector, then you can read out the dimension. Okay. So now this particular set of matrices that you have given is not generating all symmetric matrices. But suppose if you take this, suppose let's say my basis is like 1 0 0 0 and 0 1 1 0 and then 0 0 0 1. Suppose if this is my set of basis elements, then a general vector A B B A, this is a symmetric general symmetric matrix. This can be written as A times 1 0 0 0 plus B times 0 1 1 0 plus C times 0 0 0 1. Correct? So these are 3 basis elements that I require in order to develop any arbitrary 2 by 2 symmetric matrix. Okay. So this is one example. So let me now look at another example. Suppose if I say V is equal to, V is a set of all 2 by 2, okay, 2 by 2 antisymmetric matrices. Set of 2 by 2 antisymmetric matrices. What is antisymmetry? Antisymmetry is your A transpose has to be equal to minus A. Correct? That means we have to have A, B, C, D. Transpose has to be equal to, the transpose of this is equal to A, C, B, D. Okay, but this has to be equal to minus A, minus B, minus C, minus D. Okay, now A has to be equal to minus A. That means what? 2 times A is equal to 0. Since 2 is not equal to 0, A has to be equal to 0. Okay, similarly, D has to be equal to 0. Okay, and what else? Your C C should be equal to minus B, so that B is minus C. That is fine. Okay. So what does that mean? That means C and B are same, except that there is a minus sign difference. So what happens? So what will be the dimension of this vector space? Or in other words, I may have to say that this is equal to, I should say 0, A minus A, 0, such that A is in real number. So the set of all 2 by 2 antisymmetry matrices, diagonal elements has to be 0 and off diagonal elements have to be related. So what is the dimension of this vector space?
One.
Is 1. There is only one real number that is required. So this is a one-dimensional vector space, correct? So what is the basis element? The basis element is simply 0, 1, minus 1, 0. This is the basis element. There is only one element, one vector in the basis. So it's a one-dimensional vector space. Okay. So the notion of this dimension is something that you can easily understand from the number of scalars that are required to describe the vector space. Okay, so for example, let me ask you this question, because we have talked about this vector space. Let's say I have a vector space which is set of all straight lines, on a plane. Okay, so we have defined how to add two lines and things like that. So what is the dimension of this V? What do you think is the dimension of this V?
Sir, infinite.
Okay, why infinite?
Sir, there are infinite number of straight lines possible.
No, the infinite number of straight lines is different. Here also, when I say ABCD, there are infinite number of matrices, right? So how many elements are there in vector space is not important. How many elements are there in the basis is important.
Sir, is answer 1, sir?
2, sir. 2, sir.
Huh? 1, 2, why 2?
Sir.
Why 1? Okay, tell me the reason why 2, why 1?
Sir, it's 2 because it's a
one at a time.
Because, sir, 2
Yeah,
bases is
go
required.
ahead, one at a time. What? Why are you saying 2? What are those bases?
So because in a plane, two bases is required to construct.
Yeah, but that is,
line, sir.
but we are not talking about points in a plane. No, these are lines in a plane. So our vector is not a point, right? Our vector is not a point in the sense it is not an arrow from origin. This is a straight line.
So it can be 1 because we can express a straight line with one each scalar equation. Like if you want to express a particular straight line, then I can express y is equal to a. So one scalar is needed to define that straight line.
Yeah, but any arbitrary straight line can you define with one real number? Please understand this word arbitrary. Any arbitrary straight line can you define with one real number? See, y is equal to a is always going to be parallel to x-axis.
Yeah.
But that's not arbitrary, right? You can have some line oriented in some fashion also. So the question that we should ask is,
Sir,
yeah,
I think it is 2 dimensions because I need 2 constants to specify any straight
what
line.
are the
slope and the scalar. C.
very good. So that is precisely the case. To define a straight line, you require slope and intercept, y-intercept. 2 real numbers are required to define a straight line, right? So it's a two-dimensional. It's a two-dimensional vector space. Okay, so I want you to. This is a two-dimensional vector space. Now we have defined the two sets. No, so let us call this. Let me write this down. Let's say I have some vector space V1, which is equal to x, y, such that x, y are in real numbers. Okay, x, y are in real numbers. This is a vector space. What is the dimension? Two dimension, because I require x and y. The dimension of V1 is equal to 2. Now I am going to define V2. This I will call it as MC, such that M and C are real numbers. So what is this? This is also a two-dimensional vector space. Dimension of V2 is also 2, but this is set of all straight lines on a plane. Okay. Now one can think of, so you can think of making a transformation from V1 to V2. Okay, you can make a transformation from V1 to V2 such that any curve in the plane connecting these points x, y can be brought as another curve in this MC plane, right? XY is a plane, MC is a plane. Okay, have you heard of this kind of a transformation anytime?
The Legendre transformation.
Exactly. That is the Legendre transformation. That is what you do when you try to go from Lagrangian to Hamiltonian, or you go from internal energy to Helmholtz free energy, or internal energy to enthalpy in thermodynamics. So Legendre transformation is just basically a transformation from x, y to MC. That is the slope and intercept. Okay, so that is the Legendre transformation. Okay, so yeah, so the interesting aspect is that we have these vector spaces and we have these definitions. So what we tried today is essentially to generalize this notion of vector and define vector spaces. And we talked about linear dependence, linear independence, and definition of a basis, dimension of the vector space, and a very useful idea to discover the dimension of the vector spaces in general cases. Okay, so I will stop here, and we will take up this discussion from here next. I think I require one more class to describe the state space completely. So in the next class, we will generalize the notion of this vector to something called the infinite dimensional spaces, and that is where we will have to do some hard work in terms of developing the notion of Hilbert spaces and inner product spaces and Hilbert spaces. So I'll stop here. If you have some questions, you can. Yeah.
Sir, so he told Legendre transformation. So I think it is a subset of linear transformation, isn't it, sir? Like we have to say it as some linear transformation, isn't it? I mean, the more generalized name I'm telling.
No, it's not linear transformation. See, linear transformation you can always represent from a vector space to another vector space. Okay, so here Legendre transform is basically you transform a function in that vector space to another function in that vector space, not to a point to point. So
Okay.
a whole curve in XY plane will be transformed to another curve in MC plane.
Okay, sir. Sir, one more thing, sir. Go a little bit up, sir. There you defined about the linear independency. There I had one small doubt, sir. Yeah, here. Yeah, here. Here you told that alpha equal to 0, beta equal to 0 now, sir. But there is this a vector is equal to minus beta by alpha. If we put 0 by 0, it becomes an infinite form now, sir. How come we can say that, sir? I mean, I had that doubt.
No, whatever I have, see this particular box, whatever I have written here is an argument valid only if alpha and beta are not 0.
Okay.
If alpha and beta are not 0, then A and B are linearly dependent. So the only way to not to have linear dependence is to make both of them 0.
So only.
So if both of them are 0, then this box doesn't arise at all.
Okay, sir. So it's like an proof by contradiction.
Yes.
So, and one more thing, sir. You come to the antisymmetric matrix, sir. Symmetric matrix. Yeah. A little bit up, sir.
This is antisymmetric. Or symmetric.
Yeah, this one is. Okay. How do you tell dimension as 1, sir? Isn't it? I told it as 2. But how you tell as 1? Like one will be for A and another one will be for representing C equal to B. That one. So it told it as 2. But how it became as 1?
No, what I'm saying is your A and D have to be equal to 0. That is what I have argued here. A is equal to 0 and B is equal to 0. So that value is fixed. The only thing
for
is,
every antisymmetric matrix is it 0, sir?
Yeah, because your Ai has to be equal to minus Aji. Right.
Okay.
So that means Aii has to be equal to 0. All diagonal entries for every antisymmetric matrix is 0.
Okay, sir. Okay.
So the general proof is something like this. Let's say Aij is equal to minus Aji. This is our antisymmetric condition. Now put I equal to j, so Aii is equal to minus Ai. So again, so the same argument, 2 times Aii is equal to 0. 2 is not equal to 0, so Aii is not equal to 0, so Aii has to be equal to 0 for all I, because this is true for any. So all diagonal elements of antisymmetric matrix are 0.
Matrix has to be 0. So it's just that, so A, D are 0 because A equal to 0, D is also equal to 0. Then in that case, those two, B is equal to C. So for that, we need only one thing.
One, yes.
Okay, okay, sir.
Excuse me, sir.
Yes.
Sir, I just want to ask that how to get the physical institution of this vector space. Like if I want to consider physically, like I can get the idea of field with the help of electric field or gravitational field. But if I want to consider this like vector space physically, then how I can think of?
Yeah. So what I'm trying to tell you is that your feeling that you get what a field that we are talking about here is vector electric field or magnetic field. So that is also not correct, because this field is different from electric field and magnetic field. What we are defining is here a very different mathematical entity. It has got nothing to do with the electric field or a magnetic field. So if you think that you understand field by just the name appearing both sides, that's not the correct comparison or correct analogy to take. So what I want you to develop as a practice is that when we are trying to discuss these mathematical structures, we don't have to worry about how to understand them physically. Now the point is, whenever we are trying to use them in physics, there is some use, no? That is why we are using them in physics. So we have to only learn how to use them in physics. Okay. So vector space is something which is a mathematical structure, and it is very useful in physics in many circumstances. For example, suppose you want to talk about polarization of light. Now, polarization of light is basically, if light is propagating in some particular direction, the polarization can be in two perpendicular directions compared to this polarization direction. Now, the light amplitude in these two directions can be written as a column vector of two members. Okay. Now, this column vector, if you consider set of all polarized states of light, that means it will be a two-dimensional vector space. Now, it turns out, because there is circular polarization and elliptical polarization, this two-dimensional vector cannot be real. These components of the vector cannot be simply real. They have to be complex. Only then circular polarization can be explained. So if you look at the state of polarization of electromagnetic field, then you require a complex two-dimensional vector space and nothing else. That means all polarization states can be described by using elements of complex two-dimensional vector space. Now, when I define a complex two-dimensional vector space in the way that I defined today, okay, we don't foresee that, okay, this is going to be useful there. But when we try to look at polarization as a concept, then this vector space falls in place so that the states are essentially the vector spaces here, the vectors in this vector space. Then all that we know about this vector space and its structure are useful for us to describe polarization optics, and they are very useful even to find out polarization changes when the light interacts or scatters from the material and so on. Okay, so that is how I think we have to treat this one. And it's not that we will be able to give a kind of a physical picture for every mathematical entity that we are talking about.
Okay, sir, I got this. And sir, I have one question from not question, sir. Like in last class, you asked that how we can explain the interference by taking psi as a complex function. So for that, is it true to consider that we need the wave function to be complex in order to explain interference pattern, because we don't know that at what point this electron will hit the screen. So basically, we need a kind of probability density function so that we can have a kind of idea that, okay, at what bright fringe the electron will hit. And that probability distribution density function is basically given from the wave function, which need to be complex in nature.
Yeah, so I think what you're saying is, I cannot say it is wrong, but what I'm trying to say is it's not clear to me, but I want you to think along these lines. In optics, when you say you are observing an interference, what is the requirement? When do you observe interference in optics? There should be something called coherence, right? So if coherence is not there, then you don't observe interference, right? So what is coherence? Coherence is essentially a constant phase relation between two sources, right? If you say double slit, each slit is like a source, but since these two sources are coming from the same source, they are phase related, correct? So this constant phase relation between the two sources is what is called coherence, and that is what gives rise to interference. Now here, if you have two different wave functions, you will get interference only if these two different wave functions, they differ by a relative phase. That means one wave function and the other wave function must differ by a phase. Now, this phase is not an overall phase, but it's a relative phase. Now, such a relative phase can be brought about only if psi is complex. If psi is real, then there is no relative. There can be only relative phase of 0 and pi. But 0 and pi as such will not give you maxima minima. Okay, it will either give you completely maxima or completely minima. But maximum minimum will come if there is another certain other relative phase that is other than 0 and pi. So such a relative phase will come only when you, like I told you just now, that you cannot describe all polarization states if you consider only real vector space. In the same way, you cannot describe interference if you consider only the real functions here.
Okay, sir. Actually, sir, I was thinking in the terms of like probability density function, because we don't know exactly when the electron will fall at which peak of the interference. So in order to, as you suggested last time, that Max Born got this whole idea of probabilistic interpretation with the help of Einstein's idea of optics. Like so, as Einstein had told that the amplitude square will give us the probability for photons. So similarly, here also it could be like we don't know electrons without detectors. We don't know electrons is following what path. So we also don't know there are many bright fringes will be observed. So we don't know what where the electron will hit the screen at what bright fringes. So in order to find out, we need a kind of probability function. So that function can be we can get from the Max Born interpretation of the wave function, which he told to be complex and psi square should be the probability of that.
Correct. Yeah, that is fine. But what I'm trying to say is that the notion of probability is required only to quantitatively estimate the interference, whatever the intensity that we observe in experiments and this. But the interference as such will occur even, suppose let's say that you don't interpret wave function related to probability. Even then interference occurs, correct? So the interference occurs because there is a relative phase between these two wave functions that are combining to give us the probability. So what I'm trying to say is relative phase is the key word, that is the important word, and probability will come as a consequence of Bond's rule. But because of this relative phase, you get the interference.
Okay. Yes, sir, I got that idea. Thank you, sir.
Yeah. So just before I sign off, I think there was a question posted in the group by Siddharth. Is Siddharth here? Is it Siddharth who posted that question about the spin? So he had some discomfort in understanding the spin of a vehicle. So then I asked the question, how do you understand mass and charge? So I just wanted to make some comment. It's not that we are going to resolve these questions today, but let me just tell you that any property of an electron, how do we realize it? That there is a property like this for the electron. It is always, because we don't see electron, we don't have a direct access to electron. So anytime we say that electron has this property, or any other fundamental particle for that matter has this property, only by its reaction to certain or its response to certain investigation. For example, let's say I apply electric field. Now the electron behaves in a way as if it has charge. Okay. Now I apply, let's say, a magnetic field. Now electron behaves as if it has a magnetic dipole moment. So it is because of these responses that electron shows to the external applied fields that we come to understand that electron has got this property, this property, this property. Okay. So now if you are not able to understand this, that means there is some understanding that you have to modify. For example, you may think that spin is like a spinning top, something is spinning like this. If this is the notion that you have in mind, it's not wrong. Many people have this. Even now, when people teach, they say that, okay, this is spinning, sometimes up spin, down spin, like this. There are certain things, because this is our weakness, because we want to visualize things. But this weakness should not come in the way of appreciating the real concept. The real concept is that I always found it very convenient to pitch my understanding on how it responds. Now, if you understand that it is like spinning ball-like thing, then if you say it is not a ball but it is a wave, then how to understand this spin is a problem. Okay, so I do not know whether the origin of your question is related to your understanding of what an electron is, which we don't know. But if you keep, as a physics student, if you keep your understanding to the level where how do you actually first identify that there is a spin? Only by its response to an applied magnetic field. That is what Stern-Gerlach experiment is all about, which we will discuss in great detail later. But so we say that electron has charge or a spin only based on how it responds to our investigation, our applied fields. And then we say that, okay, this is what it is. Spin is a more interesting and a little complicated concept, which we will come to. But any property for that matter is only identified like this. Because we have to do only like this because we don't have direct access to see whether electron is really spinning. In fact, the concept of spin or the name spin came because initially people thought that it is spinning. That's what Goudsmit and Uhlenbach's paper talks about, the paper just after Pauli's paper. Goudsmit and Uhlenbach have actually considered that it is spinning. And then later Stern-Gerlach experiment was done, and then there's a sequence of 3-4 papers which established this concept of spin in 25, 26, like that, even before Schrodinger equation came into existence. So these are based on some notions, but it's not that. So finally, what is that we understand now is what I will be presenting to you. And that, according to that understanding, all these properties can be understood only by doing some experiment as to how electron responds. If you go to fundamental particles, like quarks and various particles, there are other things like strangeness and color. So all these things, how do you know that they are there? And what do they mean basically? Here, at least spin, you have some physical intuition. But what is the meaning of color, and what is the meaning of charm or strangeness? So these are things which are based on the response of the particles to various inputs. So this is just a comment on that question. Okay, so if there are no questions, then we can close. Okay, bye.